Hi everyone, this is Analog Circuit Design, Lecture 24, two-stage amplifier. I would like to acknowledge my PhD advisor, Michael Flynn, and then also a good friend of mine, Seung-Jong Lee, for his help. Here's the outline, two-stage amplifier. Here's the single-stage amplifier example. We already learned about this. Those are both differential inputs, so this is differential input and output. This is differential input but single-ended output, right? So both of them are single-stage amplifier. The reason why we say single stage is that here's the only like input to output. There's only one stage, right? So single stage is simple. That's good. So it's simple, which is good, but limited gain. Let's say like 20, like 40 dB. If you use like cascode or something. But in the feedback we learned that we need a high gain. High gain is usually better. So the single stage amplifier might not enough. To overcome a limitation of the single stage amplifier, which is overcome limitation of first stage amplifier, which is low gain. People use two-stage amplifier a lot. So in this case, this is a first stage, and this is second stage. And if you just draw like a simple system diagram, it's like first there is Vin, which is differential, and then this is stage 1, and then here is stage 2 and V out. So usually in stage 2 we're focusing on high output swing, which is headroom. And then the gain of this two-stage amplifier, we can just multiply two gains. So the first gain, 1, is we already learned, is GM1, RO1, RO3. And the second stage gain is GM5, RO5, RO7, right? So the overall gain, oh, there is minus. The overall gain is plus, right? Just multiply both, 2. So GM1, RO1, RO3 times GM5, RO5, RO7. So this is a lot larger than just a single stage amplifier. And the reason for focusing on high swing is so our purpose to use two-stage amplifier is for high gain. So when you think about like a cascode amplifier, single-stage cascode amplifier has kind of high gain, but their problem is their low output swing, right? So two-stage amplifier is, I mean, in terms of gain and swing, better than cascode amplifier because it has high gain and high output swing. So let me just write it down here. Two-stage two-stage amp versus cascode single stage. Two-stage amp, I mean, of course it consumes more power, but still it has high gain. Also cascode also has high gain, but it's a good headroom. I mean, it's output headroom, so good. I'll say output swing. But cascode, bad output swing. So it's headroom. So that's why two-stage amplifier has an advantage over a single-stage amplifier, which means that they can have high gain because they cascode. They connect two stages in series, so gains are multiplied, so it can have high gain. And also we can focus on high swing at the output. So like here, when you see this, there's only two MOSFET, so its headroom is good. And we can also make our two-stage amplifier as a single-ended output like this. So this is what we learned before, that a single-ended differential output, and then the output is connected to a also this is this is common source amplifier, right? Input is PMOS. We connect one another single-stage amplifier, so it can be two-stage. So as I said in the previous slide, the second stage we focus on high swing, so you can see that we only have two MOSFET stacked, so we can have high output swing. Again, the reason why we use two-stage amplifier is to get high gain, so that's our main goal, to use two-stage amplifier. And we can also think about the frequency response. So the poles, we have actually three poles, one pole here, here, here. But usually this pole is in really high frequency, and then so our interest pole is this and this. So first pole can be P out, and that's the RC constant, right? So R would be R07, R6, right? Because here R07 and here R06. And the C would be, let me just say, is approximately just CL. So here, ignore like C, D, B, 7 and 6, because we will also, when we see this node, we will see the parasitic capacitance of this MOSFET and this MOSFET, right? Let's just, for simplicity, ignore that and then just think about, consider CL. The reason is that usually the CL is large. So that's because CL is large. I mean, usually, not always, but usually. And the other one would be CPA at this node. So this node also we will just do some approximation. And what's the R? R would be R04. That's the same as output node, R04 and then R02, right? And C. So we'll consider CGS7. Well, I mean it's CA, but this is like CGS7. Also, the reason is that this CGS7 is like a large value here. So we kind of can ignore the parasitic capacitance of this M4 and M2. When we design this amplifier, this part, the size of the second stage is kind of large. So that's why in this case we will only consider CGS7. This frequency we'll cover it later, but this is usually in very high frequency, so that's not usually not our interest. So let's say these two poles, and we need to like analyze these poles because we'll focus on the stability challenge. So those two poles, which was at the output pole and then the node A pole, they are closely related to the stability challenge. So let's talk about this stability challenge. This is about like phase margin. So PM phase margin. We're talking about phase margin. Let me just briefly cover about the pole at node E. So we say it's a high frequency doublet at node E. Doublet means there's a 0 and pole 2. So I'll just write it down, the pole. So WPE pole is actually minus 1 over GM3 and CE, because this is diode connected, so its resistance is 1 over GM3, and the CE is, we can say, so let's just move GM3 to the top, and the CE can be CGS3 plus CGS4, because the CE is the CGS4, CGS3. Their summation is C, and we can just say it as minus GM3 to CGS3, because the size of 3 and 4 are the same. And also we do have 0, also 0, so 0, that's WZE is, I mean, we're not doing the whole calculation, but it's GM3 and CGS3. So you can see that the 0 and the pole, they're like kind of similar. They're very close. But here, this is very high frequency. And this is also high frequency, right? But these two, WP out, we calculated before, right? So CL times the resistor at this node, and then WPA, that's also CGS7, because this is like a large transistor usually, and then times the resistance here, so this. So this is for low frequency. Saying is this WPE is located at higher frequency than these two, and what we're doing is focus on WPA and the omega P out for phase margin. Okay, and with those poles and 0, we can draw a bullet plot. What was it? So we have WP out, right? And that one was CL, right? And we also have omega P out, PA at node A, that's which is here. So we're doing RC constant. We will multiply RC constants. There will be RO4, RO2, times CGS7 and 1. Usually this is the lowest because the CO is large. So say lowest since CL large. So let's draw a bullet plot. It's already drawn, but the first one. Okay, so this one is omega p out. It's like the lowest frequency. Why? Because CL is large. This is omega p out, and the next one, that's omega pa. Okay, so this one is here, this one is this, and we also have another pole which is at high frequency. So this pole, that's the third pole, and this is omega pe. And we also have, if we just draw a further, we have 0 again. So at this point there's omega 0 and E2. But as we said, when we talk about phase margin, we will have to focus on these two early poles. So to consider phase margin, when we will look at two low frequency poles. And what are they? They are WP out, omega P out and omega PA, right? And what about the phase? So at the first pole, the phase at this point, that's like minus 45, right? And then in the second pole, I mean the drawing is not that accurate, but the second pole, this is minus 138. And if it goes further, and this one, this red dotted line, that's minus 180. So what was our condition to be stable? Okay, so to be stable in feedback system, when phase is minus 80, the gain should be less than 1. That's our goal, right? The gain should be less than 1. And then this is gain 1, where 0, I mean, because it's dB scale, so here's 0. So gain should be less than 1, right? That's our goal. And where is this? And that part is this part, right? When phase is minus 180, then the gain should be less than 1. And do you see is that true? No. It seems really large, right? The gain is really large at this time already. So this, with this just poles, this is unstable. And you know, this is loop gain. Maybe I can just remind you one more time. The reason why we discuss about phase margin is that we are dealing with feedback system, and then the feedback system does look like this. Let's look like this, and minus and plus, and then there's an amplifier, and then this is out, V out, and V in. In this circuit, they are not connected, right? If we connect this V out to this input, then it will be a unique gain buffer. But at this time, we didn't connect the feedback. But when we think about phase margin, we need to look at the loop gain. So, this is loop gain. And so loop gain is coming back here. This is loop gain, right? Loop gain is A beta. So that's why this is A times H is, well, I mean the transfer function of amplifier. So I'll just say this is also beta A omega. Okay. That's why we're looking at it, because we are going to use this amplifier, two-stage amplifier, in a feedback system, and that's why we want to see the loop gain, and then the loop gain is here. So if you don't do anything here, they're usually this P out and PA, they are like maybe like close enough, so it's not easy to make this system stable. So I'll say this system unstable. Okay, so in the previous slide we said that two-stage amplifier is unstable, and let's just review again the stable feedback system. So this is from the previous lecture. We want to look into more about when the phase margin is 45 degree. Again, we're looking at we're talking about this feedback system, because if you don't use feedback system, then everything is just stable. Since we're using feedback system, because of the positive feedback, we are worried about positive feedback, and that's when the system can be unstable. So when we have 45 degree phase margin, that's how it should look like this. So the first pole is here, right? And then the second pole should be at the unit gain. That's how it works. So in the first pole, that's minus 45 degree, and this will be minus 90, and then when in the second pole, that's 138 degree, and then you see that the gain is already 1, and then you see that the gain is already 1, which is 0 because we're using this log. So this is how the phase margin is 138. So again, so we assume two-pole system, and then for 45 phase margin, the second pole, in this case, second pole is omega p2, should be on the unity gain axis right here, right? So that should be unity gain. So for example, assume A0 is 1,000, and then beta is 1. What is the omega p2 in terms of omega p1? This is a good exercise. So what happened is in this part. This part, what is it? This is minus 20 dB per decade, right? So in decade. So what happened is beta A0 will go down by 20 dB per decade. 20 dB per decade, what does it mean? It means 1/10. So every decade, whenever the frequency becomes 10 times, the gain becomes 10, 1/10. So let's just write it down in an easy way. So it's like 20 log. I'll just remove the absolute value here. So 20 log beta A, like 20, and this, this should be what, 10. That's omega p2 and omega p1. So this is the equation. If we just directly interpret this value, then this is how it works. So let's see why. I'm assuming that this this value, the log, this dB is minus 40. I mean just 40, assuming that this is 40. So assuming that, for example, EX, if that's 40, and we want to make this 40 dB, we want to make this to 0 dB, right? How many decades? Because every decade, the gain decreases by 20. So it needs 2 decades, which means the frequency becomes 100 times freq. That's how it works, right? So that's represented like this. I mean, you can stop the lecture and then calculate on your own. So if you just calculate this, and then 20 is just removed, and then 10 log, that's just beta A, and that's omega p2 and omega p1, right? So that's why omega p2 is loop gain times omega p1. So in this example, since 1001, it becomes 1000 omega p1. That's how it works. So what we've done was, the gain is there, the loop gain is beta A0, and then after this first pole, the gain decreases by 20 dB per decade. That's how pole works. If there's one pole, then we just pass one pole, then 20 minus 20 dB per decade. And what we want is, our goal is to set our phase margin as 45, right? So we want to have to increase, I mean, our pole should be at the unity gain, right, to achieve this. So our omega p2 should be large enough than this omega p1, so we can make this gain to 1. So that's how it calculated. This part is kind of confusing, can be confusing. So you can stop your lecture. I recommend you stop your lecture and then calculate these things. So the result is this, the unity gain frequency is just pole times the pole frequency times the gain. Let's draw a pole in the plot. So this would be out, because out is the slowest, and this would be PA, and then we will have at the high frequency omega PE, and then more higher, a little bit higher actually, like just twice. This would be omega Z0 at E. But at this moment, when we think about phase margin, we only need these two. Okay, so we'll only consider about these two, focus on these two low frequency poles, and this part, let's just ignore. Let's just ignore the high frequency part, because we're talking about phase margin. The problem is the main poles, which is low frequency poles, they're too close. As you see in the previous slide, to get a 45-degree phase margin, for 45-degree phase margin, WP2 should be beta WP1, right? Which means two poles should be a lot different. But here they're too close. That's why the circuit is not stable when we apply a feedback system with this. So again, this is P out, this is omega P A, and well, you know, there is omega PE at the high frequency and 0. But let's just focus on this, as I said. So we are going to zoom in. zoom in. So zoom in this. So we're going to have omega PA and omega P out, right? So to make feedback system stable, we have to separate these two, right? How much? For, again, for EX, for example, phase margin 45, WP2 should be, actually should be large, equal, or let's say larger, should be larger than loop gain times omega P1, right? So we need to separate them. There's a multiple way. The one way we can do is move this to here. So it's like move this pole to the lower frequency. Maybe this is not intuitive, like if you want to make it far away, then why don't you just make this closer to here and then make this farther away. It's kind of not easy, because for this one, this is load. To make this closer here, then we need to increase the load, and then that's not that like efficient, because the CL is already really large. And there's the other reason, that to make this pole like lower, slower, that's easier. So it's easier to add cap to node A. If I say the answer, Miller effect. So we can use Miller effect in node A. So that's why we add more cap at node A, which means adding more cap means making it slower, right? To make this slower frequency. So this part, just write down this higher frequency, which is fast. Okay, and this one is 0 DC, so it's slower, low frequency. So adding cap at A is easier, so we're going to move this pole to a lower frequency so we can make more space between two poles. So here's the jargon that we use, like a term that we use: dominant. Make pole at node A dominant. So dominant means it's low frequency. So it's lower. It's like when you see like this. Let's say we see some bullet plot like this, pole 2, and this is omega pole 1. We say this lower frequency is dominant pole. So we want to make this node A, which is in higher frequency at this moment than PL, but we want to make this to move to a lower frequency to add capacitance here more. Here. So we want to do this omega P out and omega P A, and we want to make this to a lower, to move to a lower frequency. Let's say I have a little more like this lower frequency, so we can have more space between them, right? So more space. So that's what we call a compensation. So frequency compensation. So frequency compensation, what we discussed was we need to make a dominant pole, right? So basically there was like this this frequency, and then there was omega PA, and then there's omega P out. There's two close. So what we can do, first one is push a pole lower in frequency by adding cap. That's what we're going to do, and then that's the frequency compensation. So this will go like far away here. And the second one, the other thing is push other pole to higher frequency. So we're not going to actually to make something faster means we need to increase the current, right? That's the easiest way. Like for example, here to make this faster, then we may have to increase the current, which means we need to decrease the resistance, or something like that. But we're not doing that. Our main goal, main way to compensation is move this pole to a lower frequency. But interestingly, if we done this pole will go faster. It's like a bonus, and then we'll discuss it later. But the point here is that we're going to do this one, omega PA to lower. We are adding additional cap. That's what we're mainly discuss about. So to achieve phase margin 45 degree, then what we need is omega PA should be a lot slower than omega P out, right? Because you see that this omega PA goes too slow. That's what we're gonna do, and that should be beta E 0 and on omega P out. And when we see the omega P out, PA is like approximately minus 1 over CA, well, CCA, and R04, R02, and omega P out is approximately CL, because CL is the largest, R07 and R06 over 1. So to make this, assuming that beta E0 is 10,000, then it turns out like CCA, approximately CCA can be 1,000 times CL, like for example. But this is huge. This is huge. Which means that we need to add this value intentionally at node A, and this is really huge. This is huge. So it's not like plausible just adding CA, just adding more additional capacitance here, like 1,000 times more than the CL. That's too much. It's extra. So that's why we're going to use Miller effect. So use Miller effect to multiply capacitance. It's because it's C equivalent becomes 1 plus AV times CC, right? Because of the Miller effect. So basically it's what it does is node A and then C equivalent. Yeah. Here's B, then B. So that's what we're doing. We're going to use Miller effect to amplify, to multiply the capacitance. Increase the effective capacitance. So this is how it looks like. This one is Miller effect. The capacitance, the intentional capacitance to make omega A slow, right? So this capacitance, again, I just repeat the goal. Goal is add, it's more like make omega pole A slower, which means add cap on node A. That's our goal. So if we use this Miller effect, let's say, so here's the first stage. So this is the first stage, right? So this is the first stage, and this is second stage, right? So from the first stage output, which is A, if we add capacitor at the output of the second amplifier, then we can get a Miller effect here. So we are connecting these like this, and we call this, it's a very useful Miller compensation. We are adding cap, and then it becomes very large by Miller effect. So we add cap here, intentional. So this is not parasitic, this is intentional actual cap. We add cap here, so we can do slower, make moves down like a PA. That's what we did. But also, interestingly, it can also moves omega P out up. So that's an interesting part. And then we call this as pole splitting. So let's focus on this part. How can we make this pole faster by adding this cap? Before discussing about this V out making the pole adhere faster, let's just write it down this as an equation. So WPA is, let's say we have a cap here, which is the original cap CA, right? It's like RA, the resistance looked from node A times by the capacitor at node A. So one will be CA, and then we will have an extra cap by using Miller effect, right? And that becomes like this, right? That's minus AV2 A2, and C equivalent is AV2 times CC, right? And this omega PA can be rewritten as minus 1 over, what's the RA? Resistance looked at here is this 2 parallel resistor, right? So that's RO4, RO2. And the gain is GM7, RO7, RO6, right? Because what we need is the second stage gain, and then the second stage is here. Second stage, right? So that's it. This times CC and plus CA. That's our new modified, intentionally make it slower, right? A new dominant pole. So this is dominant pole. This is dominant pole now. Dominant means the slowest, which means slowest. I mean lowest. And here's the interesting part, the pole frequency at omega P out, because we discussed in the previous slide that this omega P out is getting faster, right? So this is our circuit now, and CC is pretty big. So CC is pretty big, and well, here's V out. So in a high frequency, what happens is, I mean high enough frequency, I'm saying is compared to CC. High frequency, that becomes short. That looks like short. Why? Because the impedance of capacitance is 1 over SCC, right? So S is frequency. If we increase frequency, then its impedance getting low. So what happened is here CC looks like short at high frequency. Because when we talk about the Bode plot, so this is omega PA. So we are already over that omega PA, and then somewhere is like omega P out, right? So at this region, I mean, CC looks like oh, let me just write it down in red. So in this region, CC looks like short. That's what we're looking at. So the pole omega P out, again, what we are looking at is in terms of Bode plot, we already passed this omega PA. We're looking at like this omega P out in a faster frequency. In this region, we can consider the CC as short, and now we can calculate the omega P out. So that will be minus, what's the resistance here? So this is diode connection, right? So one is like 1 over GM7 and parallel R6 R06 and times CL and plus CA, right? Because now it's short. It's shorted with CCA2. But this one is, because 1 over GM7 is a lot smaller than R06, so it just become 1 over GM7. Let me just, because this is ignored, so what we got is 1 over GM7 and then CL plus CA. This is, so what was our original value without WP omega P out before adding CC? That one was 1 CL. So when we compare these two, this is larger, so it's bigger. Why bigger? Usually the CA is smaller than CL, so the CL or CL plus CA, they are kind of similar. But when we compare about this 1 over GM7 and then this R07, R06, this is a lot large. So this is a lot like slow frequency. So I'm saying is, let me just say, it's like a faster frequency, a higher frequency. I mean, that's faster, right? Higher frequency, and then the original one is a lower frequency. So like, I would just say slow. So what you can see is by adding this CC, the omega P out becomes faster compared to our original before adding CC. So to wrap up, by adding this CC makes omega PA slower, lower, and then omega P out faster. And then here's the equation that's changed because of the CC. So that, and then that's post-splitting by adding CC, which is also Miller compensation. So far, we talked about Miller compensation to improve phase margin. So this compensation is improve phase margin, but it can cause a problem, which is zero. It can generate zero from that feed-forward path. We briefly covered about this zero in a previous lecture. So it basically two paths from node A to V out. So and then that can cause a zero. So first one is the two path means through M7. So it's like a through GM7, right? Because if we like stimulate node A, then M7 the current will change, right? The current. So it's like a just a gain, right? The common source amplifier types of path. And there's the other path, which is CC. So this path is the other one. So the first path is here, and the second path is through this compensation cap. Again, this compensation cap is a additional intentional cap that we add. And because there are two paths, we can show it can show zero. So in the feed-forward path, they have a zero because of this path, feed-forward path. And this is actually a common source amplifier. So this is source and this is gate, and because this is PMOS. And in the Razavi book, chapter 6.2, they already calculated the zero of the common source amplifier. So again, this is common source amplifier, common source amp. So the zero is omega 0 is plus GM over C GD. So here this polarity is important. This is positive 0, which means right hand plane 0. So let's redraw our CS amplifier. Now we just are using an MOS here, and then as I said, we do have this 0. The 0 is omega 0 is GM over CC, and then this is, as I said, right hand plane 0. And we'll discuss about why this is bad. Let's draw Bode plot first. So we have one pole and one zero in this case. So the gain would be here. So DC gain. What is DC gain? When we consider DC gain, we can just ignore every capacitor, right? So DC gain is GM RL RO, right? Because here is RO. And when we meet pole, then the gain decreases, right? And this is like minus 20 dB per decade. And the phase we'll see at the pole, so it's here, and that will be 45 degrees. So the phase is like this, and then the phase decreases further, and then here it goes to minus 90. So here is 90 degree, and then after that we meet 0. When we meet 0, the gain increases by 20 dB again. I mean, the slope increases 20 dB again, so it becomes just flat. But the phase changes again. The phase becomes another, experience another minus 45 degree. So at 0, we see another 45 degree phase change, and it goes all the way to minus 160. So it's like this. So this is what's happening, and then the reason for this is so omega is actually, let's say AS actually looks like, because we have one pole, right? It's S omega P, and then we have 1 0, but note that the polarity is plus, so this is how it looks like. The key point here is that both of them, both 0 and then pole, impact the phase in the same direction. Why? Because when we consider phase, if something is in a denominator or I mean the numerator or denominator, they have an opposite impact on phase. So because this numerator 0 has the opposite sign compared to this, so they're impacting the same way to phase. So what I'm saying is the pole also decrease the phase, and then this right hand plane 0 also decreases the phase. So both of them decrease the phase by 90 degree. And it turns out the RHP 0, right hand plane 0, is really bad for OPM phase margin. Again, when we talk about phase margin, it's a feedback system, right? Feedback system. Like whenever we like phase or stability, that's all about feedback system. So the first pole will be pole PA, where we did a Milli compensation, and then the next one will be Z, the 0, and the other one, the next one will be the output pole, and then the fastest pole is at the node E. What happened to phase is at the first pole it will be 45, right? So that's a 45 degree, and at the next 0 that will be minus 135 degree, and then next this pull out, that's minus 225 degree. So it's just going down all the way whenever they meet pole or 0. So when we talk about phase margin, so phase margin is, the definition of phase margin is when the loop gain, what is loop gain? Loop gain is beta A. Loop gain is 1. The phase. So, well, I mean, phase margin is the phase to minus 180 degree when the loop gain is 1. So it means that when phase is 180 minus 180, the loop gain should be lower than 1. So RHEP0 adds negative phase. So negative phase is bad, right? Because we don't want our phase goes to minus 180. But the worst part is, but it increases the gain. So it's even worse than pole. It's really bad. Why is it even bad for even worse than pole? Pole, so here pole will adds up as phase, but at least decrease the gain, right? But zero, it's phase up and gain up, and this is the worst scenario, right? Because we want our gain is lower than 1 when phase is minus 180. So the RHP0 is really bad for phase margin. Well, luckily there is a way to fix this RHP0. So the first way to do to solve the RHP0 problem is we can move 0 to higher frequency. So why is it better? Why is it good if you move 0 to higher frequency? Because if 0 goes to higher frequency, then the gain is already like very low, right? Because of the other poles. So its impact is negligible. So what we can do here is actually there's a cap, and then we can add resistor. So C and like resistor 0, RZ. And if we just do some math, what happened to this is it's 1 over GM7 minus RZ and CC. So if we set like RZ is like close to, I mean, of course we cannot make it exactly the same. If you make the RZ close to 1 over GM7, then omega Z will go to infinity. I mean, ideally. So it means that if we add resistor here, resistance here, then this sneak path, the second path, is less effective because the 0 happen when there are two paths, right? So by adding this resistor, this path is getting weak, so less 0. Instead of resistor, there's the other way that we can also do. Maybe we can just put some MOSFET rather than resistor, but it's not like good. So it's like V bias, and omega Z will be, I mean, this is the same, right? So it's like M2, this is M2, if we say MZ, so MZ in triode works like RZ. Well, but this is not like accurate, so just don't do this. So just use R resistor, not this way. And there's the other way that we can remove this 0 impact. I mean, eliminating 0 is that we can put some buffer here. So so this is CC, and then this is gain 1. So what it does is still gets Miller effect. Why? So the way how Miller effect works is the voltage difference, right? I mean, if voltage moves here like this, and then the other way, the voltage should move like this. So because there's a huge voltage difference between these nodes, we can see the capacitor like kind of larger. I mean, the effective capacitor looks larger, right? So what we do here is that we just want to copy the voltage V out to here by using buffer. But if you use this buffer, but the buffer blocks the feed forward path, which means is that because we are using buffer, the signal cannot go to this way because of the buffer. So as I said, the way how to eliminate zero is that we can just eliminate this feed forward path, then the zero can be eliminated. Because zero is made when there are two paths. So that's why we just want to remove this signal path, and then buffer can remove it. So by doing this, no zero. What we can do, this buffer is we can use source follower. So for buffer, for this buffer, we can use source follower. The way how it looks is, so this V out, so this is the input and this is the output, right? So maybe it can be like this, and so it's like here, V out, and this can be input NMOS, and we have some current source, and then this. So this is how we can implement it. For example, like this. So this is source follower, right? This is source follower. Source follower. When you see this scheme, this voltage is copied to this one, right? Because this is V out. Because this is source follower, and then the gain of source follower is 1. But the signal from here to here, they cannot go, right? Because this is just gate. So that's like a one-way direction buffer. So and then we can implement it like this. But this method is not that effective because it's difficult for low voltage design. Due to the MOSFET operation region. But anyway, this is also an interesting way to eliminate zero by adding one directional buffer. Next, we'll talk about compensation trade-offs. The trade-off is between phase margin versus the current in second stage. That's what we are going to discuss. Pole position and phase margin. In this slide, we'll assume that we need 60-degree phase margin because usually PM phase margin 45 is not enough. So lots of cases people just use phase margin as 60 degree, and let's say beta 1, because when beta 1, that's like the worst case. I mean, assuming when beta is smaller than 1, then beta 1 is worst case. I mean, the larger the beta, then worse phase margin. So we have a first pole here. So this part is first pole, and then this is the second pole. So which one is dominant pole? So this is dominant pole, right? I mean, it's simple. Dominant pole means the the lower frequency pole. So to get a 60-degree phase margin, what happened here is that we need this part 90-degree, and this part should shift 30-degree, right? So this is for phase margin 60. So in total 120-degree, 120-degree when gain, I mean the beta A. So actually this is beta A. When beta A is 0, A, I mean it should be frequency beta A S is 1, right? So that's the definition of phase margin. When the loop gain is 1 and the phase is 120, I mean this is minus 120, then our phase margin is 60. So it means that omega u and omega p2 should be tangent 30 degree, and so that's why we put this as omega u. So when omega u, it means omega u is a single gain, right? I mean, again, the beta is 1, so when the frequency is omega u, when the gain is 1, and then if you see the phase shift about minus 120 degree, then our phase margin is 60. So to get that, this is what we need, and it turns out omega p2 is square root 3 times omega u. So you see the difference between, so this is when between, I mean, phase margin 45. So this is when PM is 60 degree. But I mean, we already discussed that when meanwhile, if PM is 45 degree, then omega P2 was omega unity, right? Just for comparison. So if we need more phase margin, that means we need to put this pole 2 higher than omega unity. It means that we have to make the circuit faster. Our second pole should locate it in the faster region, I mean in the higher frequency. So to write it down again, for PM60, phase margin 60, then it means the non-dominant pole, which is pole 2, should be square root 3 times omega unity gains here, loop. But for some safety margin, we can set like omega p2 to 3 times unit gain frequency. So to just review this bullet plot, what happened is this is like a loop gain, right? So this is loop gain graph, and in this case beta is 1. So loop gain is here, but if we make a unique gain buffer, that's when beta is 1, right? So unique gain buffer, so this is, since this is dB scale, this is at the 0, and then it just goes here, and then at unique gain this frequency, it decreases the gain. So basically this is like a 3 dB bandwidth for our closed loop. We can also approximate the unity gain frequency. So let's say unity gain frequency, unity gain frequency is omega u, that's what we used. Or like we can just also say loop, and then assume the first stage pole is dominant. So this one is A, node A, and then we're going to assume the first stage is that 5T transistor. This one. This one. This amplifier. So the gain is, the first stage gain is GM1, RO4, and RO2. Now you can just refer to the previous slide about the schematic. That's the gain, and then if we just draw a bullet plot, so this would be omega PA, right? The dominant pole. And this is omega U, unity gain frequency. And then what's the gain? So this is loop gain, right? This is loop gain in dB scale. The loop gain is first GM1, RO4, RO2 times the next one, the next stage gain, AV2 times AV2. And so the omega PA was 1 R2 RO4, and then RC. C was, we have a Miller compensation, right? So that will be AV2CC. We just ignore the parasitic capacitance here because this AV2CC is a lot, larger than that. So with this, we can calculate the unity loop gain. So omega unity is this is the gain AVDC times the dominant pole, omega PA. And we do have both of them, so omega PA was, let's just ignore the sign here, RO4, AV2, CC, and then AVDC, the DC gain is GM1, RO2, RO4, and AV2. And we see a lot of common terms, right? So we can just remove this and this. So it turns out CC GM1. So as a conclusion, omega U unity gain is GM1 over CC. Now let's represent the second stage pole. So second stage pole means high frequency pole. By the way, the reason why we're just representing all this pole in some certain equation is that if once we done this, we can see some trade-off between those frequency. So the PL, omega PL, we already calculated, that's approximately GM7 and CA plus CL. CA is the parasitic capacitance at node A, and we we can again one more approximate it by CL GM7 because CL is usually a lot larger. I mean, like every time, a lot larger than CA. So we can just approximate it. And then you may wonder why we don't see CC in our this calculation. Let's just review it again. So this calculation is coming out from so that was node A, and then we have CA, and here's the PMOS, right? Here's a PMOS, and then we do have this Miller CC, and there was V out, and we do have CL, right? So the capacitance at node here, the total cap is, well, basically this cap and this cap, right? So from this number one cap, the one pass cap, if we just represent it, that's a series connected cap. That's SCC1 plus SCA1, right? And that will be SCC plus CA. Well, I mean, we need to multiply it. SCC, CA, and CC plus CA. So in this case, the C equivalent, which is the number, the one path, C equivalent becomes CC plus CA. Okay, so this CA, so CC plus CA and CC times CA. But CC is a lot larger than CA, right? So it becomes CA. So it becomes CA, right? Because CC is a lot larger, we can just remove this CA, then CC can be just canceled out, and then we only see CA. I mean, it's kind of opposite to the resistor parallel connection. So that's why there's no CC. CC is not shown because it's larger than CA. So we got this non-dominant pole representation. So now what we can do is we can set the GM ratio here. GM ratio. Let's brought up the things that we calculated. So for phase margin 60 degree, we want this square root 3 times omega u, a unity gain frequency, and that should be our second pole. So let's say just for safety choose, we need 3 times of unity frequency. What was the second pole? So that was P out, and that's minus GM7, C, and CL. And what was the unity gain frequency? U loop, that's GM1 over CC. So if we just replace this to here, to insert here, then we got GM7CL is 3 times GM1CC, right? Then it gives GM7, GM1 is 3 times CC, CL. So usually CC is larger, I mean CL is larger than CC, but like in some book, maybe let's say the recommendation is CC is like CL over 2, the half CL. And this, it turns out the GM7, GM1 should be 6. So which means this branch has 6 times larger, needs 6 times larger transconductance. And that means the second branch here, the second branch needs 6 times current, right? Similarly, if we say we need more phase margin, like 70 degree. In this case, we need 3, and for safety choose, let's say we need like 4 times a higher frequency than unity gain. I mean our non-dominant pole, and this is pole 2 is pole out, right? So if you do the similar calculation, that gives us 4CLCC, which means GM7 should be, I mean let's say should be GM1 8 times 8, means the second branch needs 8 times current. So what it shows is if we need more phase margin, we have to flow more current in the second stage. We can also explain it like this. As we said, the way how to get a phase margin, right? To have a phase margin, what we should do is we need to split the 2 poles, right? So the first pole is kind of constant at the low frequency. Then what we have to do is we have to make pole 2 faster, right? We need to put this pole 2 to the higher frequency. That means we have to make the second stage faster. I mean our CL is fixed because CL is a load capacitance, and then that depends on the next stage. So it's more like that's assuming that that's fixed. So to make our second stage faster, then we have to flow more current. So let me just write it down again. So intuitively, I mean it's just a natural way. I mean the obvious way to explain. So to get more phase margin, we want omega P1 and omega P2 far, right? We want them further away. So since omega, if omega P1 is fixed, then we should do then we need to make we need higher here omega P2. It means that faster second branch and more current. Yeah, that's how it works. To get a phase margin, we need to flow more current on this second branch. So to summarize today's lecture, we introduced a 2-stage amplifier, and that was single-ended differential amplifier, right? And we also talked about stability challenge, because in single-stage amplifier there's no stability issue because they cannot shift the phase enough. Their maximum phase shift is 90 degree. But if we have 2-stage amplifier, they have 2 poles, we can shift the phase to 180, and that can cause the instability. And then we also do a compensation for phase margin because two-stage amplifier can suffer from stability issue. So we do a compensation, and then what do we use here? Miller compensation. So we intentionally put cap at Miller node, and after that, if you do a Miller compensation, we can see also a zero problem, and then zero is really bad for phase margin. So we fix the zero by adding resistor. And then after that, we talked about compensation trade-offs. This is between phase margin versus second stage current.